Hello everyone. So today we see a very beautiful theorem, or you can say the result from the linear algebra. So let me state here first what is this. So the theorem is basically, so let we have a matrix, square matrix, of course, of n by n over the field F. So we have a n cross n square matrix over the field F, and also let's say we are assuming that and also we are assuming that suppose all eigenvalue, all, it's a very important that all eigenvalue must be all eigenvalues of A are in F. So then the A can be written as the sum of two matrices D plus N, where D is a diagonalizable matrix, where A is a diagonalizable matrix and N is an important matrix. So now these two matrices are very nice. The diagonal matrix and the nilpotent matrix, both are very easy matrix. You can easily multiple two diagonal matrix. You can calculate any power of diagonal matrix comparably easy way. So in general matrix, if you take a general matrix and want to calculate the uh, the power of the matrix, it's a difficult. But if you have a diagonal matrix and you want to calculate the power of the diagonal matrix, just you take the power of the diagonal matrix. Similarly, nilpotent matrix, here the nilpotent matrix will get this nilpotent matrix will have the speciality that we see here. So of course, let me tell you before prove this theorem. So I'll give you a proof. So let me tell you the so this is important, that diagonalizable matrix. So this part is the diagonalizable matrix. So now the thing here that so let me tell you the nilpotent matrix. So firstly, I'll come to the proof. So let's say we have a matrix. I call, let's say, a matrix. Say a matrix M is called a nilpotent matrix. Nilpotent matrix of index, it's a small k if k is the smallest, of course, if such a k exists, smallest positive integer, such that a to the power k equals to 0. So this is the definition of nilpotent matrix. Now see, so let me give you example of the nilpotent matrix. So let's say I'm taking here the matrix, let's say M. So you can take example this one, that M suffix n, I'm taking the, so let me tell here. So okay, all right, so I'm going to the according to the degree, order. So M2, I'm taking that 0 1 0. So then you can check that M2 square equals to the matrix 0 0 matrix. So it has index 2. Similarly, if you take M3, it's like this, that 0 and let's say displace something. All right, so I'm putting here 1 1, then 0 0, and 1, then 0 0 0. If you take this matrix, then this matrix has, so M3 square, it will be a 0 matrix. So 0 0 0 0 0 0 0 0 0 0. Of course, from here we are getting a pattern that in general, if we take a n by n matrix, of course, this form that will be a upper triangular matrix. You can say the strict upper triangular matrix. Of course, the entry here in the place one, you can take any number, but I'm taking this for the convenience because in this theory you will get this type of matrix. That's why I'm writing here. So in general, you can find out a nilpotent matrix. So in general, this type of matrix, let me write here, it is n by n matrix. So all the entry are zero. So in general, any strictly upper triangular matrix of order n is in nilpotent matrix is a nilpotent matrix of order. So all right, so this is not order. So of nilpotent matrix of index n. So this is you can take it as a note. So this is note. So of course, this theory tells us that we have an important matrix for every of index n for every n greater or equal to 1. Now, okay, right. So of course, the nilpotent matrix, and we are taking the non-zero nilpotent matrix. These matrices are all. So of course, let me and non-zero nilpotent matrix. This type of matrix are the non-zero matrix and nilpotent. Zero matrix is trivially nilpotent. Okay, so now come to our next, actually our original theory. So the proof is here of the main theory. So before proof, let me again read the theorem. So we have a matrix A, of course square matrix, where the all eigenvalue of A are in the field here. Then we want to say that the matrix A can be written as the sum of two matrices, where D is a diagonal matrix and N is a nilpotent matrix. So that actually we'll see. So I'll tell you what actually this theorem tell us, the significance of this theory. I'll tell you later. So, but let me prove first. So since all eigenvalues of A are in the field are in F, so there exists a non-singular matrix singular. There exists a non-singular matrix. Of course, the non-singular matrix P such that P inverse, A field. This is a so this is equal to, you can write here, this equals to basically the upper triangular matrix. So this is a upper triangular matrix matrix upper triangular matrix with diagonal entries are eigenvalues of A. Of course, this is, and now the proof. What is the proof of this statement? So you can check the abstract algebra by the abstract algebra, the proof. Of course, the linear part by Hurston. You can check the Hurston book, the linear algebra part. That if you have a matrix which all the eigenvalue are in the base field F, then that matrix is of course similar to a upper triangular matrix. Now, once we know this, what we can say, we will deal with the upper triangular matrix from now. So, of course, let me write here that if you take a upper triangular matrix, for example, 2 by 2. So you take here A, let's say here, the B, and here C and 0. This is observation, you can say. How we can represent upper triangular matrix. Now see, upper triangular matrix, we can write A0 as a sum of diagonal matrix and the nilpotent matrix. This is diagonalizable. You can say diagonalizable because diagonal matrix, and this is nilpotent. You can check because I wrote here the theorem that in general any strictly upper triangular matrix of order n is a non-zero nilpotent matrix of index n. Of course, so this is true now. So now you can take here A, let's say I'm taking here A, B, and C. Of course, 0, D, and let's say here we have E, and then here I'm taking 0, 0, and F. So this is, of course, a upper triangular matrix. So you can also write here A, 0, 0, 0, D, 0, 0, 0, F. So then, and this part will be basically 0, B, C, 0, 0, 0, of course, D, and 0, 0, 0. So similarly, this is a diagonalizable matrix. Diagonalizable matrix, and this is, of course, the nilpotent matrix. So this observation tell us that any n by n matrix in general, upper triangular, of course, upper triangular matrix we can write as the sum of the diagonal matrix. So yeah, diagonal matrix plus the nilpotent, right? So we can write all of this that if you give me if you take any upper triangular matrix, that matrix you can write as the sum of diagonal matrix and nilpotent matrix. Now see here, if you go to this part, then what we're getting? We're getting that basically here that from this observation. So let me write here. This is 1. All this is 1, and this is, let's say, all this is 2. So by 1 and 2 we get, by 1 and 2 we get that of course the P inverse AP equals to a diagonal matrix. This is a diagonal matrix plus here we are getting here of course that this is the nilpotent. So where because in the place go to this in the part 1, the upper triangular matrix we can replace by diagonal matrix plus nilpotent matrix, right? This is diagonal, okay, matrix, and each nilpotent. So far it is clear that just so now both sides if we multiple by from the left hand side we multiple by P, and from the right hand side we multiple by P inverse, both sides. So then we get here that we apply the distributive property because matrix multiplication distributive property. So what we get here P inverse, then here A, and then this is P inverse. So this is basically P inverse, and then this is basically P and P inverse. So right, so of course because right, so let me write here the notation that let me change D1 and this is DN1. So this is 1 I'm putting here because in my statement I put D and N, so that's why I have to replace this. So this is identity, so we are getting A equal to basically D plus N. Now where D is basically D is P D1 P inverse, which is a diagonalizable matrix. Diagonalizable. This is a diagonalizable matrix. It is clear. It's a diagonalizable matrix, and we don't know this is nilpotent or not. P of n1 P inverse. So let's say, and let me write here, and let me write here the n equals to this. Now, one thing is clear. In the theorem, we state that if you go to the theory, we state there that D is the diagonalizable matrix. Yes, we got it. Now, this n part we have to prove it is nilpotent, and here it will be because this part is nilpotent. So we will just check that this is nilpotent. Now, since n is nilpotent, and the P inverse, what was it? Yes, P and P n1 P inverse. So this is basically this to the power any k. So of course, let me write here, and to the power any m if we put in this, so then it will be what? P n1 P inverse whole to the power m, and we know this is nothing but P n1 whole to the power m P inverse. So nilpotent means this n to the power some power 0, and that power if you take in the place. Okay, so n1 is nilpotent, and then this, so n is nilpotent. Why? Because n1 nilpotent means n to the power something equal to 0. So here, so now you that power sec m, so now if you take n to the power m, that also give you 0 because of this calculation. So nilpotent. So what we are getting? We are getting that A matrix equal to D plus N, where finally you put this, where D is a diagonal matrix, diagonalizable, and N is important. Okay, so this is the result basically. So in this proof, actually in this theorem, when in the proof we use basically this theorem from the linear algebra, that any matrix whose eigenvalues are in F, then that matrix can be similar. That matrix is similar to the upper triangular matrix. Now the proof is basically, if you go to the first hand book, you can see there that they basically use the quotient space concept and the induction. So yeah, but I'm not going to the proof. Just believe that we know this theorem, then only that needed, and then that upper triangular matrix can be written as diagonal matrix plus nilpotent. So using that fact, we can prove this result. Okay. So we have it now that any matrix can be written as the diagonalizable matrix plus nilpotent matrix. So now here main interesting point that so see, A equals to what? Any matrix if you take, let's say all the eigenvalue are in the field F, then you can write it as a diagonal matrix plus nilpotent. So this is diagonalizable and this is nilpotent. So clearly, if n equals to 0 matrix, then A equals to GD, so each diagonalizable. So this means diagonalizable. So this means, so that's why if you take a matrix and if you want to check that matrix is diagonalizable or not, so then what you need to check, inside the matrix the A, you have some nilpotent part. If that nilpotent part not appear, then okay. And we know the nilpotent matrix is not diagonalizable, okay, except it is a 0 matrix. So therefore, when the matrix A diagonalizable, the matrix A, then that situation the nilpotent part will not appear, okay. And of course, this decomposition will be somehow unique. I'm not going to that direction, but it is important here we learn that important fact. If you have a matrix and all the eigenvalues, are in basically in the given field, then the matrix can be written as the sum of a diagonal matrix plus a nilpotent matrix. That is very important here. Okay, so yeah, that is good result. So now, yeah, that's all. So see you in the next nice video. I'll make one more video on the construction of the real number system. That will also going to be interesting. But today is enough. And thank you so much. Good night.